Okay, welcome. Now I want to go for the stereographic projection. We had with Corbusier sunset, sunrise, sunset, sunrise. We had our circle, space, time, space, time, space, time. And we had this perspective projection, which went from night to space, with the preservation of the covering area. And now we continue to make the other projection. It's a stereographic projection from space to time. And this preserves the area. So we will go in detail to characterize this projection. So we are with the gnomon, with the perspective projection in bright sunlight. So, and at sunset, we go to the sky, not with the sun, but not with the linearity of the sun. We go with the circularity of the sky at night. So therefore we go from here to here, from space to time. So and it works like this. Horizon. We have the circularity of space at the sky. We have this point, and our problem is to make a line in time. Good. With that, we are not with Galileo or Bruno or Kepler. We are with Ptolemy, and we are with the Enlightenment of the 18th and 19th century. Good. So we are not with the Copernican term, as I think we experience for 120 years now. That's just the inverse. Good. The key problem with this is, so what can we get from spatiality to make a proper step in time, to get to linearity? So if we have these circles and project that, so the interesting thing is that the only thing what we can keep, if this is there's a circle, however it is on this circle, this will project a circle on the ground. I made a small program here. You see a circle on a sphere, which is the spatiality, projects. So this is what you preserve from space. What you see, what you can see from space is this angularity, the angles of the circle. This is what is preserved. And move it. It's a small program. It's very slow in the cloud. Change the latitude. Let me see. The YouTubes will show it very interesting. It's a little dirty code, but it's working and shows how it works. So, like the complexity we developed here it's more complex than it looks at the first glance. So what we preserve with this example with a circle shows that we preserve the angles. So, which means any point here preserves its angles. So we have the unity of all angles. So which I think this is a description of what Leibniz called a moment, which has no parts. Because the problem is the moment that we preserve all angles. So unity with the monads, and this is in mathematics, it's called the boundaries. So the unity of all angles. The problem is, there's always a consistency. So as in the gnomon, where the stick all time collapse at a single point in space, here all space collapse in a single point in time. Because the problem is, the moment you expand this thing, if you're not just with the circles, you have distortions. And it's very, very funny, displayed in a funny way with this YouTube. If you want to put that into a flat map, you have to cut it. And you can't get it flat. So which means you're here and you have to cut it, which is called, so and if you want to go in more details, you have to cut it again. And you have to cut it again. So in an infinitesimal way. And this is called branching. So to get a straight line, it's a real problem. Yeah. And all arithmetics, all calculations, all computing is about getting straight lines on flat line. From out the circularity of space. To get a proper step, next step, straight on flat ground. And this problem is called branching. And what you have is boundaries. And the unity of all angles. So very abstract concepts, but I think it's interesting to look at this because, so here we have maps, for example, the Dymaxion map of Buckminster-Fuller. It just cuts the planet at the oceans and keeps the continent connected, but each of these triangles is a massive distortion. You have to go to infinitesimal small cutting of everything to get it straight. Here he stays on top of his map. There's a lot of geographic tools and functions in Mathematica available. You can look it up. But the interesting here is how to look at maps. And this is an interesting thing as well. So this is the branching. But you see, these branches are And this is very fascinating. We really like that, these styles. But these are traces in time. Yeah. Or we have the same with the fascinosum of the fractals or the cellular automata. This, for example, Mathematica has a lot of cellular of these stuff, very simple at hand. This, for example, is a line, line of code you need to render this pattern, which is a pattern of growth. So it's of time. So this is what I showed in this diagram when you're throwing a stone into water, and then you have the synchronicity of the waves, which takes space, and then the time which cuts it. So what we see with all these maps is that time. We see the development of time with all the maps. This is called branching, and the complication of how to look at, or what to see, what your eyes, the eyes of time. So this is what I said. Every line, every graphics is with the eye of time. You cut space because space is an auditive entity. So that's it. Yeah. So what you keep from space is your boundaries. You preserve the angles, so it's a unity of all the angles. It's always 330, and you keep that. This is in proportion. When there's a certain constellation where you can keep the circles and the sphere in a certain, where you can keep then the distances as well, and make that circle preservable. But when thing's flat, without distortion, it's not possible. You always have to cut space. So time cuts space. And you have the eyes of time to see something. And you cut space all the time. And if you do a straight line, this is a sequence of cuts to make it straight. Good. As we had with the perspective drawing, the counterpart is construction. And in my reading, I think there are good reasons for that. It's very surprising. So if we think these unity of angles, so the boundaries, and the branching, which is growing in time, is how things work, then the beginning of time is the origin, and that's the gravity of space. That's interesting. Newton, for example, said that gravity is the skin of God. So I think with this perspective projection, gravity, if time goes in a single line, gravity is the beginning of time, minus gravity is the end of time. That's here. Expand first the start, and the end, where everything is balanced. And you cut everything into dust with branching. So to go for construction, for example. Now, take for example point 1, 2, 3, 4, 5. 1, 2, 5. You want to make a hanging chain, as we do in construction. How to read that? I would say, as we have the branching here, we simply say beginning of time is here, end of time is here, where things are in balance with gravity. And I will show you, that's it. So I will show you how this works in code. Switch off the video. So we take these 5 points, we fix point 1 and point 5, and we fix it in x direction, but in y direction we give it a variable. So we give a certain strength or elasticity to the connections of the points, and we put forces to point 2, 3, and 4 vertical with the gravity of 0.2 and no wind or horizontal movements. So this is gravity. Now we make equations. We simply say gravity equals this is for 0.2, so 0.1 minus 0.2 multiplied with the elasticity or the strength, plus, that's one vector to the preceding point, the other vector to the succeeding point with the same elasticity. These two vectors should be equal gravity. We do it with the third point and with the fourth point as well, with their neighbors. So Mathematica, so this talks with to the ears of space. This is the quantum geometry, gives you these equations. And you see 3 equations, gravity on the left side, those. And then here, 0, this is the coordinate, the x, this is the x. And then you say in y, it's this variable y1, y3, 3, 4. So we have 3 variables, 3 equations. We can solve that. So we want to get the solution for y2, y3, y4, which meet these 3 equations. We solve that. Then we get the coordinates y2, y3, y4, which means we have these points. Put that to the eyes of time, and we get the hanging chain. If we put the gravity, it's to the gravity, but the strength of deflection, so if we take that as deflection, not as hanging, put that to deflection, so the strength of reinforcement, then we get this load. And if we draw that, then we get this enforcement as you know from civil engineering. That's it. And I think finite elements, maybe a stroke, and so on, just this. So it's running toward the end of time. Always like this. Branching, flowing, growing like this fungus in the beginning, towards the end, towards a finite balance. So this is a comprehensive version of this code. For example, here we can go for 36 of these elements, and then you see what's looking like this. Or in 3D, with the 2D version, 3D, same setup. You can look it up in a lecture last semester, last year. I think that's it. So to summarize, yeah, if we are in space, time. We say this is day, night. These are these are the stories, or here are the dreams. The preservation here at day is the area, the angle. This is what we can trust in. So this is what we can learn from the prior setup. We had this. So to go from TS to S star, the next scale of space, we have to trust the area. If we go to the next level of time, we have to trust the angles of speciality. Area of chronology. Angle. So we have the perspective. And here we have the stereo. So these are the dreams, the last night, the area. These are the memories, the last day. And this, interestingly, is geometry. This is arithmetics, and the calculus and computers. This is with numbers. This with the eye. And this is here. This is with symbols, characters. That's it. Enough for a discussion. Thanks for watching. See you.